Welcome to San Francisco. The AGU Fall Meeting is taking over the Bay Area, and AGU TV is here to join in. Stay tuned. Hello and welcome to day one of AGU TV. I'm your host, Juliette Goodrich. The AGU Fall Meeting is the largest Earth and space meeting in the world, and we are here to bring you the latest news. Today, we're talking with some of the biggest newsmakers. We're also touring universities and organizations doing cutting-edge work in science. Joining me now is Dr. Robert Kopp. He is director of the Rutgers Institute of Earth, Ocean, and Atmospheric Sciences at Rutgers University, and thank you so much for joining us.
Thank you, Julie. It's a pleasure to be here.
Well, a lot of changes, climate changes for one. Can you tell us about the recent update to the AGU Climate Position Statement?
The last climate change position statement came out in 2013, so it's been 6 years since this till this new statement. And a lot has happened in the time since then. There's been the Paris Agreement, the IPCC special report in 1.5 degrees warming, the fourth National Climate Assessment. And so AGU thought it was time, in light of all those changes in the broader world, to take a look again at its own position statement.
I know we're at a critical point now, so what brought up this update?
Yeah, so it was a result of all of these factors, and there's a few key changes in here. So for the first time, AGU is calling this a climate crisis. And the shoe really fits there, right? A crisis is a critical turning point in the history of an event. And we are really at a critical turning point in the history of our species with respect to climate change. And AGU wanted to call that out and recognize that there is a need for urgent action on climate change now.
Urgent action for everyone.
For everyone, yes, right? So we're calling for mitigation and adaptation action led by individuals, by governments, by business leaders, and we're also calling on scientists and engineers to engage with all of these sectors, and on academic institutions, including both funding agencies and university, to provide more resources and more focus on research, application and dissemination addressed towards addressing the climate crisis.
And you've touched on it, but why is this update so important right now?
Well, as I said, we're really at a critical turning point, and we now know, that climate change is really changing everything on the planet, right? It's an economic crisis, it's an ecological crisis, starting to impact national security, and so this statement goes through all the lines of scientific evidence which have been reviewed and refined over many decades. So we've seen it in the IPCC and the National Climate Assessment and so forth, and then takes it to look at what do we do now, and what is the special role that scientists and engineers and our institutions can play.
Does it go into detail about what do we do now?
There's a few things as a society we need to do, right? So the first one is get global net carbon dioxide emissions to zero and sharply reduce emissions of other greenhouse gases. So that means expanding energy efficiencies, it means decarbonizing the electric grid, it means decarbonizing other elements of the energy system, and also addressing all the things beyond the energy system that emit greenhouse gases. It also means taking more deliberate and careful action to adapt to the impacts of climate change.
All right, Dr. Robert Kopp, thank you.
My pleasure.
AGU TV tours some of the best organizations in the world doing exciting scientific work. Let's begin at the Iowa Flood Center.
IIHR, Hydroscience and Engineering, is an academic research center that focuses on hydraulics, hydrology, fluid mechanics, environmental science, and water sustainability. The mission is to provide both fundamental academic research to improve the engineering and scientific community, but also to do applied engineering and really help the engineering community move its engineering design forward.
Historical record, what it suggests is that the frequency of flooding across Iowa and large areas of the central US has been increasing. So one of the questions that we ask ourselves is the increase that we observe in the records, is it due to natural variability or is it driven by greenhouse gas emissions and anthropogenic climate change? The flood of 2008 made us wonder what kind of effect climate change is going to have on flooding over Iowa and over the central US.
For many, many years we were studying river mechanics, hydrology, everything about fluids and fluid flow. So, recognizing this expertise, the legislators called us to action. They said, could you help? And of course we said yes, we could. And they established the Iowa Flood Center and here at the university in the College of Engineering. Understanding the river network and its statistical and other properties allows us to build efficient and effective hydrologic models.
I'm looking into power law distributions to fit to flood data, and we chose power law because it has similar self-scaling attributes that river network topology has, and river network topology is what governs the transportation of water.
Over the years, we realized that we need an effective way of communicating our findings to the general public of Iowa. The internet, of course, that's the main vehicle to do this.
So we developed Iowa Flood Information System at the Iowa Flood Center. It's up and running for the last 8 years and serving the public of Iowa. IFIS is a one-stop web platform for communicating flood-related data and information, including flood forecasts, flood inundation maps, rainfall, and weather information. And it deals with large-scale data sets, so we are processing over 50 gigabytes of data per day and dealing with operating a flood forecast model that solves over 1.5 million differential equations to understand the flood conditions.
The Iowa Watershed Approach is something that that I think many of us have tremendous pride in here.
Floods don't really behave across neighborhood boundaries or city boundaries or county boundaries. They behave in watersheds. So if we want to understand how floods work, if we want to get in place solutions for floods, we should be doing that at the watershed scale as well. And so the Iowa Watershed Approach includes fundamentally a new idea about what if we focus on implementations in the upstream areas that can result in reduced flooding downstream.
In the Iowa Watershed Approach project, we work very closely with watershed management authorities as the local governance structure. We develop a hydrologic assessment. We work with planning consultants to create a 25-year plan for the watershed. The watersheds have hired watershed coordinators whose job it is each and every day to wake up and make the watershed a better place. We work with voluntary landowners and the watershed coordinators to find suitable locations for conservation practices. And now across 8 watersheds, we'll be building $40 million roughly in conservation practices. And then from those projects, we use our monitoring equipment and mathematical models to quantify the benefit for the benefit of these conservation practices on reduced flood damages.
A lot of times we think about flood disasters in terms of how much water or the degree of damage or the economic cost. But what about the social equity implications? With social vulnerability research, a big part of it is understanding the processes, but another part is building quantitative measures that we can use to understand how bad the problem is.
Over time, we developed a very strong brand name. The state agencies contribute to funding elements of our system. We always tell them that because the federal agencies in particular are constrained in their mission by the acts of US Congress, we have more flexibility. So often if they have some ideas and they cannot act on those ideas, we can.
It's really amazing to be a part of something that's a lot larger than me and to be involved in research that could potentially really positively affect hundreds of thousands of people. No matter where my career takes me, I know that the Iowa Flood Center has helped instill this desire to be a part of important research or projects.
We plan to continue serving the people of Iowa. There are significant scientific and practical issues that we need to address. So if there is something that we can do here within the state, that we should take care of ourselves. And when it comes to flooding and hydrology, water quality, we absolutely have the right expertise.
My name is Reed Maxwell. I am a professor of hydrology in the Department of Geology and Geological Engineering here at the Colorado School of Mines, and I direct the Integrated Groundwater Modeling Center. The big question that I'm working towards is how much water do we have, how much fresh water do we have, and how fast is it being replenished? Groundwater is really hard to observe, it's really hard to work with. We have just these very localized places where we can drill wells in the ground and sort of see groundwater directly or observe its pressure and infer its movement. And then we have some very interesting and novel techniques to infer how much groundwater we have, either from changes in storage, from changes in the gravity vector from space, from satellite remote sensing. And we use a lot of hydrologic modeling, a lot of groundwater models coupled to land surface models to understand and bridge that gap between this small scale and this really large scale. We tend to be very focused on technical details and communicating with other scientists, writing journal articles. We have our mechanisms of communication, but they're very kind of inaccessible to the public at large. And it's really enjoyable to be able to communicate what we do to a broad audience. And, you know, school kids are awesome.
Very astute. But why else? Where does water want to flow?
Education and outreach is a top priority for the Integrated Groundwater Modeling Center. When we go to these events and see the type of enthusiasm that we saw today, it really hits home with us. It really solidifies why we do what we do.
Today we were explaining different groundwater systems, kind of how groundwater flows and the negative impacts of pollution and the difficulty you can have extracting and treating that pollution. They really like it when we let them play the bad guy, and when we do that we give them a syringe of dye and they inject it into our groundwater model, and they can see, they can see very visually this plume of what we're calling pollution, right? It's just a general term, and they really like that visual.
These education and outreach experiences are so important and can really be valuable to our undergraduate and graduate students here at Mines as well as other universities.
One of the things about Colorado that's kind of cool.
It really teaches them skills in communication, changing behavior on the fly, all kinds of skills that are really useful in science in general. What we're doing is we're really instilling the importance of this early in their careers in the hopes that they will continue to engage with their community going forward.
Thanks everybody for standing out in the snow. We're going to learn about volcanoes.
Today we make a trash cano by sticking a small trash can in a big trash can and basically letting liquid nitrogen boil and expand, and then it explodes water up into the air. And the kids freak out, the kids love it. There's water in the air, there's ping pong balls flying everywhere. It's a great thing for the kids.
I've never done a trash cano in the snow. It did create a few extra challenges, but it also created a lot of fun too. It's science in action. So we talk about volcanoes. A lot of kids haven't necessarily seen a volcano in action, but they can really relate to the boom and the explosion and this material getting thrown up out of something due to a pressure change. So it's now part of my repertoire. I've taken the show on the road a lot.
Now, another big aspect of our center is research. That's mostly federally funded and mostly funded by the National Science Foundation.
So I'm an aqueous geochemist. My specialty is studying how water and rocks interact chemically.
My research interests focus on evapotranspiration in mountain regions.
I am really interested in how rocks break down or weather.
My interests in research are ground and surface water hydrology and the modeling of those systems.
We have a lot of people who do a lot of different things, study a lot of different areas of geology and geological engineering. So the center, I think, represents the best of what we have to offer in terms of collaboration and solving problems by using many approaches, many minds.
We have a small community, and so being able to collaborate with people across campus in material science and physics. I have collaborations with professors in all different departments on campus. Right before this, I was in a laser lab. And so you can't make those connections as easily at larger universities.
We also do a lot of continuing education, a lot of tech transfer between research that happens here at the School of Mines and other places, and industry, government, other agencies working and consultants working in practice who want to kind of keep up and keep current in a broad range of groundwater and hydrologic modeling.
We've really built a program that we can be very proud of, and we are very proud of it. And I think we have really high hopes for the future, great plans, and I think we can just continue to do really great things.
The Department of Earth and Environmental Sciences was born in 2012 at the University of Milano Bicocca. The strategy of our department is to develop and improve researches, maximizing synergies between the two areas of earth and environmental sciences. Our inter- and multidisciplinary approach is based on a threefold concept: understanding the mechanism influencing climate changes in the past, monitoring the present assets, forecasting future scenarios to evaluate the impacts of climate changes on the environment, and suggest effective mitigation actions. We aim at generating scientific knowledge, technological infrastructures, and advanced initiatives in education with positive impact on local, regional, national, and international socioeconomic realities. Our department includes 40 geologists, 20 biologists, 15 chemists, 5 physicists, and 3 engineers, working together from glaciology to geodynamics through atmospheric chemistry and ecology.
The Geodynamics Group at the Department of Earth and Environmental Sciences investigates the long-term evolution of climate through a focus on plate tectonics. Sedimentary basin, mountain belts, volcanic arcs, oceanic ridges, they are all expressions of plate tectonics, and they all have a huge impact on the geological carbon and water cycles which control climate on our planet. We study rocks from within these environments through a range of disciplines and techniques because they are the fundamental archives of information, and we investigate these rocks through field observations, numerical modeling, physical and chemical laboratory analysis. This is also what we teach our students in the Geological Sciences bachelor, master and doctoral degrees. They learn how to read the rocks just like a book and obtain their information regarding the functioning of the Earth system and the evolution of the Earth.
A deeper understanding of past climate changes is essential to assess the impact of human activities on climate and anticipate future climate changes. Ice cores have become one of the golden standards in paleoclimate research, thanks to their ability to archive climate information, such as greenhouse gases, temperature, and atmospheric impurities. And they allow us to study glacial and interglacial cycles. The focus of the glaciology and paleoclimate group of DSAT is the study of aeolian mineral dust deflated from the continents and transported to the polar regions. By looking at the geochemistry, mineralogy and microphysics of dust, we can get a lot of information about atmospheric circulation changes, dust sources, and environmental conditions at the sources. All this information is then put into global climate models, which include also the dust cycle. The concentration of mineral dust in polar ice is extremely low, and particles are very, very small. For this reason, at the Eurocold lab of DSAT, we have dedicated environments and clean rooms where the risk of sample contamination is reduced at minimum.
In our department, we study the sedimentary record from marine cores, looking at assemblage variations of microfossils like coccoliths, silicoflagellates, diatoms, and forams, and we analyze geochemical proxies in benthic archives like mollusks, corals, and calcareous algae to reconstruct paleoceanographic and paleoclimatic changes at high resolution. An important expertise in our team is also related to seafloor imaging and mapping using geophysical data like bathymetry, backscattering, and seismic data, coupled with underwater videos and bottom sampling to investigate geomorphic processes in the submarine environment and their interaction with benthic organisms.
We study the impacts of climate change on freshwater and terrestrial ecosystem and on biota. Lakes are extremely sensitive to pressures that operate at the global, regional, and local scale, making them good sentinels of environmental change. We are studying the different pathways that cascading effect of changes in air temperature and precipitation have on water temperature and vertical mixing regimes. These trigger the distribution of nutrients, dissolved oxygen, and other compounds in surface and deep waters, that in turn control pelagic food webs. We are analyzing the responses of aquatic communities to anthropogenic impacts to develop tools for the management and conservation of freshwater ecosystem. We are investigating the effects of climate and habitat changes and the introduction of exotic species on the ecology of population in order to propose effective measures for long-term conservation of wildlife biodiversity. We are studying how, in mountain areas, ice melting during war period can increase habitat availability and high elevation and across the tree line for alpine plants.
In our department, the atmospheric research passes through different disciplines. The main target of our research concerning the aerosol direct effect is related to the black and brown carbon aerosol. We developed an experimental method able to quantify in any sky condition the heating rate induced by light-absorbing aerosol. Our campus is the first site in the world where the heating rate of black and brown carbon is experimentally determined continuously in time. The experimental heating rate was measured from Europe across the Baltic Sea, the Atlantic and the Arctic Ocean, showing that the heat trapped in mid-latitudes can be transported till the North Pole, amplifying again the Arctic amplification and warming.
Global warming and other effects related to climate change, such as the increase of frequency and intensity of rainfall events, are expected to boost geohazards and have a large impact on water and energy resources. For monitoring, we are developing a new lab called GEMMA with advanced monitoring tools such as drones equipped with thermal cameras, hyperspectral cameras, ground penetrating radar and a laser scanner. With this tool we can monitor and survey the effect of climate changes in alpine areas, the evolution of landslides and rock glacier, and the degradation of permafrost, which are very important for geohazards. We have developed numerical tools and strategies that we can use for the modeling of these effects and that we can test against laboratory physical models or real-world case studies. A good example is offered by the Gallivaggio landslides that occurred in 2008. We can use numerical models in order to replicate and understand the dynamics of these phenomena. This allows us to improve our forecasting of potential future landslides and geohazards in light of risk assessment and risk management.
We offer 6 courses, a bachelor and a master in environmental sciences, in geological sciences, an international course in marine sciences, entirely in English, and a master course in chemistry, and finally a very interesting PhD program. Here students are an active part of the team and learn how to study the Earth system processes relevant to and responsible for the evolution of our planet and ongoing climate changes through fieldwork, laboratory activities and modeling. We are confident that our multi- and interdisciplinary approach will develop cutting-edge research in science, providing a 360 degrees understanding of environmental and climatic change.
The Department of Geosciences in Potsdam is the strangest department you will ever see anywhere in the world, because it's not just a group of professors who work together in the university. We have a unique situation where several external research institutes are also linked to us, and professors who are part of the university work in these research institutes, which means that our students have access to research facilities at the university, but also research facilities in external institutes. We have 30 such institutes linked to the faculty.
The disciplines that are present at the University of Potsdam are quite diverse, so it's pretty exciting to discuss research with colleagues as well. My research is earthquakes on volcanoes, and we also study volcano analogs and associated hazards such as subglacial floods. We work with arrays to track moving sources to record weak signals, and we also have exciting new instruments which are rotational sensors, and we can use them to combine them with a normal seismometer to hopefully get array-like results, and we're like one of the few groups worldwide that actually have these sensors.
My topic is geological remote sensing, and I am working with remote sensing imagery and Earth surface processes, ranging from optical data to radar data or laser data, and we are using all of those different techniques. And the combination of this makes it very unique to study the Earth's surface and understand, for example, erosion, debris flows, and the impact on the infrastructure characterizing natural hazards, understanding landslides, understanding the impact of earthquakes.
So one thing that I'm working on right now is combining both geochemical estimates of erosion rates, for example, with remote sensing proxies, and we're developing new remote sensing proxies that we can then validate with these geochemical methods. And that's one thing that's really great about the University of Potsdam, is that we actually have the infrastructure here to do both. We have state-of-the-art geochemical labs and also the computational power to process this data.
This institute is a unique place to work in because of this combination that we have of really top-level scientists with this setup of labs that are absolutely top-level. My research area is trying to tackle the problems of what's happening at depth in terms of fluids involved in plate tectonics, involved in mountain building processes. And in the last years, we worked hard to make Potsdam a real hub for this kind of investigation.
I'm a structural geologist working in East Africa. I'm working on the extensional tectonics in the East African Rift, more specifically in Kenya. And I study the extension of the rift, and we use drones to generate high-resolution elevation models. And we have basically drones and survey equipment for every different task we need.
What is great at the University of Potsdam is that we focus in various applications. So we can develop our methodology to many topics. Here we have actually the instrumentations, which is state-of-the-art. For example, with the georadar, we send an electromagnetic pulse inside the ground to detect structures. And with students, we try to develop and to explore new ways to collect the data to get more information into, for example, archaeological targets or water content in the soil.
The 3D capabilities that we have here are for visualization and for analysis, meaning that we can dive into the three-dimensional world in that way and that we can perform analysis on the point clouds as if we would be in the field. So it's both for educational purposes, that we teach the future generation how three-dimensional structures look like, but also for analytic purposes. The Institute of Geosciences has 120 incoming bachelor students every year, and we have about 20 master students starting every year, and we have a large number of PhD students, more than 50 PhD students that are currently at the department.
My research project is carbopaths, and we are focusing on carbonates at high pressure and high temperature using different high pressure techniques. It's really nice to do the PhD here because we have a laboratory full equipped for doing this kind of research, but also we are close to different institutes that can allow us to expand the data or the experience that we want to do.
I think the University of Potsdam is a great place to study because the University of Potsdam has a lot of instruments that are vital for field research, like for example drones or GPS instruments that we need to, if we go to the field, to collect high precision GPS points or drone data during drone flights.
Innovation in teaching is a core feature of our faculty, always has been. Research-based teaching is what we do. Every student at bachelor level is involved in a research project of their own. Every student at master level is involved in a research project of their own. Fieldwork is core, laboratories, so that we can actually get all of our students to actually be involved in measuring things themselves.
I would like to have the future generation of students understand what it means standing in the field and reading the rocks, but also being able to quantify processes using modern remote sensing data. The other thing that makes it unique is that this is a growing university with still lots of potential for growth, and that makes it unique to establish a strong geoscientific educational program.
Thank you all so much. It is really thrilling to be here today. Happy 100th birthday. That's incredible. When was the last time you looked up? My journey to medicine, to space exploration, to engineering, to 100-Year Starship, to being on this platform talking to you today started when I was a little girl on the south side of Chicago, lying outside and staring up at the stars and the sky. 100-Year Starship is about making sure we have the capabilities for human interstellar flight in 100 years. Not a launch date, not a rocket, not the vehicle going, but the capabilities. Because it's all about boosting innovation. The challenges of interstellar flight mirrors the challenges we face on Earth. Because when you think about it, we're talking about producing and controlling enormous amounts of energy. All around the world, we've looked up at the stars. We've looked up at the clouds. We wondered what they were. They were the jumping off point for so much of what we wanted to do. I like to think of ideas as potential energy. They're really wonderful, but nothing will happen until you risk putting them into action, until you change things. And right now, with this 100 years and this transition into inspiring the future, all the things that are happening at this conference, they're wonderful ideas, but nothing will happen until you take that potential and you put them into action.
Thank you very much.
Joining me now is Harriet Festing. She is the Executive Director of Anthropocene Alliance. And Harriet, thank you for joining me.
Thank you. I appreciate the invitation.
Absolutely. Let's start by talking about your recent work as written up in the Surging Waters Report.
Right. So thank you. So let me just tell you a little bit about Anthropocene Alliance. We are a non-profit based in Florida, and we help people harmed by climate change and environmental abuse. And we do that largely through our network, which is called Higher Ground, which has become the largest flood survivor network in the country. So we work with 45 flood survivor advocacy groups in 22 US states. What's kind of particularly interesting about them is that around half of them are low wealth, African American, Latino, maybe Native American, often impacted by a broad range of environmental injustices. Not just flooding. And around half of them we have matched with pro bono scientists through this incredible program called the Thriving Earth Exchange, which is run by the American Geophysical Union. And so that really was the content of the report, Surging Waters, where we talked about some of those scientific partnerships that we're developing with flood survivors who you can imagine. So around a third of the flood survivor advocates that we work with have actually lost their homes. They've had to evacuate as a result of the flooding. They're in horrific circumstances, often with no solution to the flooding that they are facing, and with new development occurring on top of that, climate change. And they're fighting these battles without the scientific knowledge that cities, that politicians have access to. And so we're giving these residents access to science so that they can go in and start to argue for the kind of solutions that they need. And those are the kind of, we describe some of these case studies.
Absolutely. All right, let's talk about your presenting and the topic, Science as a Weapon in the Battle Against Environmental Injustice. Expand on that.
Okay. So one of the things that we've discovered as we work with scientists and flood survivor advocates is that there's a tension. I think it's widely recognized by scientists that science is absolutely critical for public and environmental policy, that you cannot tackle climate change, excessive heat, flooding, drought without this broad range of scientific disciplines, meteorology, geology, hydrology, and so on. So that's well recognized. The tension comes with recognizing that public and scientific policy, public policy and social policy, i.e. politics, is also critical and in fact inextricably linked with science. Scientists are really uncomfortable with this idea of politics, but they actually operate within a context that is highly political. And really that's what I'm trying to do. I'm trying to get them to realize that of this system, that this context that exists, and that they need to embrace that and recognize it.
All right. Well, Harriet Festing, thank you so much. Appreciate your time.
Thank you.
The School and Observatory of Earth Sciences of Strasbourg has three main missions: teaching, research, and observatory programs. Our five main themes are continental lithosphere dynamics, water resources and fluid circulation, especially in the context of global change, reservoirs, and in particular geothermal resources, lithosphere dynamics, especially earthquakes and seismicity, finally deep earth and its structure and processes. We record and provide geophysical and environmental data from metropolitan France and from other places in the world, including Antarctica, in many different fields. These include seismology, magnetism, gravimetry, geodesy, and environmental geosciences. EOST hosts bachelor's, master's, and PhD programs in many earth science fields, including geology, geophysics, and environmental geosciences. We run the only French engineering diploma in geophysics. This involves theoretical and practical teaching by industry and academic experts. The university campus here is extremely dynamic and is very beautiful. The same can be said for Strasbourg itself. We are located in the center of Western Europe, and so very close to other universities in France, Germany, Switzerland, the Netherlands, and Belgium.
Our research addresses how the Earth's surface evolved through geological times and what are the drivers of these changes. The surface of our planet is highly dynamic because the Earth has moving tectonic plates and it hosts an atmosphere, biosphere, cryosphere and hydrosphere. Climate is a major driver of environmental changes as illustrated by the dramatic shrinking of Lake Chad in the past, today and maybe tomorrow. Geologists find evidence of ancient ice sheet over Africa. This shows that continental drift also drives changes of surface, but at geological timescale. Landslides are both a process that shapes the Earth's surface and a geohazard that cause risks and damage to the society. The precise timing of the evolution of continental environment is a major issue. That's why we are running a lab of geochronology using cosmogenic isotopes and uranium series.
In a context of global change, we investigate alteration, weathering, and water transfer processes in continental hydrosystems. We develop multi-scale biogeochemical and isotopic approaches to understand mechanisms and processes in the critical zone. Specifically, we focus on 4 topics: the processes and reactions that determines the properties of water-mineral interface, the history of formation and evolution of alteration profiles, the exchange and transfer between soil and vegetation, and the transformation and transport of micropollutants in soil and at the catchment scale. We benefit from the technical support of Biogeochemical Analysis Center dedicated to soil and water chemistry, fluid mineral interfaces, and isotope measurement. To evaluate and predict fluid circulation and water resources, we combine laboratory experiment with field experiment, especially on our observatories, monitor for more 35 years for the Steinbach catchment in the forest and for more 20 years in the Vineyard catchment of Ruffach. The development of hydrobiogeochemical model includes advanced computational techniques, inverse problem, and uncertainty analysis.
A key question in earthquake science is to understand what controls the behavior of active fault systems, what regions are prone to experience large earthquakes, and the problem is that fault processes span a very wide range of timescales. Now, a recent game changer is the explosion of near-fault observations, which is a new opportunity to better capture the accumulation of strain over centuries, over decades. Over much shorter timescales, we can also combine various datasets to constrain how this accumulated strain is then released by earthquakes or slow slip events. We can also investigate links between magma and the activation of faults or earthquakes. For example, we can use new earthquake detection location techniques to track how magma migrates in volcanoes.
In the Alsace region of France, we're very, very proud of our history of geothermal energy exploitation. Since the 1980s, there have been many wells drilled into the area, some of which are as deep as 5,000 meters. The reason why there's so much geothermal energy in the region, or energy exploitation, is that they are exploiting a thermal anomaly and also a hot natural brine within a fractured and therefore permeable granitic basement, which acts as the geothermal reservoir. We work very closely with French geothermal industry. Geothermal research is also funded by the National French Research Agency. I work in the rock deformation laboratory to supply rock physical properties of the geothermal rocks of the area to inform on numerical modeling, heat flow modeling, for example. Our strength measurements in the lab can also help with borehole stability assessment and also stimulation strategies.
Accessing the deep Earth interior is difficult from the surface, so we need continuous and precise observation. At AOST, we have developed seismic tomographic techniques that provide us with quantitative image of the lower mantle. We can also use some gravimetric and geodetic and magnetic surface observations. So for instance, from magnetic observation, we can reconstruct core flows at the core surface. Going deeper into the Earth's core is more difficult. The inner core has some oscillations that we have never detected till now. Gravimetric magnetic, seismological and geodetic observatories are all very important to have a chance to detect small signals coming from the Earth's deep interior. And particularly global coverage is very important. So stations like the one in Antarctica are fundamental in our research in the deep interior of the Earth.
In conclusion, we conduct innovative research in geosciences, especially looking at the links between deep earth processes and surface processes, natural hazards, natural resources and environmental geosciences. We provide a unique international teaching environment that combines university programs, an engineering school, and doctoral programs with very active research teams.
We want to know how our planet is changing, to understand different processes, different chemical reactions, and how the system all work together to make a sustainable planet for humankind.
We hope to help citizens figure out how to adapt to the climate change that's already here, but perhaps most of all to mitigate it, to transition out of the fossil fuel age to something better.
The choice we make can impact the generations to come. If we can all work together, we can solve the problem.
The Center for Global and Regional Environmental Research was started in 1990. A group of faculty, maybe a dozen or so, had been meeting and talking about this new idea that we could actually be changing the climate. Out of that, the state legislature decided to fund a center looking into questions of climate change, funded by a tax on utilities in the state. We use that to be a research center as well as do education and outreach to the citizens of Iowa. This is the 8th Iowa Climate Statement. We try to get all the scientists to agree on a climate statement that's unique to Iowa, that helps to inform policy in Iowa, also helps to inform citizens about what climate change might mean. We're going to experience much, much warmer conditions, much more severe flooding.
The Iowa Climate Statement is a good way of building consensus among scientists and then communicating that information more broadly to the public. If we're able to start to show Iowans how our local climate is being impacted by climate change, hopefully that will start to spur some local action to make a difference.
The mission, I would say, is to foster interdisciplinary research, including all aspects of sciences, both the natural sciences, the engineering, social and behavioral sciences, and even humanities. Most of our center does mathematical modeling. In my own case, modeling of agricultural crops and soils and how they are responding to climate change. But experimentally, we try to remove carbon dioxide, greenhouse gas from the atmosphere.
I work with high-protein microalgae, and I'm growing it to be a sustainable cattle feed. In this case, this is a resource recovery project. Microalgae is something valuable that we're growing, but we're growing it with simulated power plant emissions. The microalgae is capturing the CO2, it's something that's not being emitted.
My PhD research is about how we can use plants that accumulate a lot of nickel to make other useful materials, like energy storage materials or wastewater treatment materials. Places that have been polluted with metal, we can actually take the metal out of the soil and bring it back to a more natural state.
My overall research area is in developing sophisticated models that can be used to analyze air pollution. The real focus on climate change has been greenhouse gas emissions. But it turns out that aerosols, these particles that are air pollutants, they also play a tremendous role in climate system. Black carbon, coming from diesel engines or forest fires, they actually absorb solar radiation, so they act like a greenhouse gas. Where we have air pollution and weather in the same model, we can find that the black carbon, say in a city like Delhi, because of its warming agent, makes the atmosphere more stable and can actually increase the the pollution levels because the emissions are not mixing as high into the atmosphere.
What I'm doing is called smoke plume rise. We calculate the injection height and then the model releases the fire emissions in this altitude. Models that don't include this parameterization, they release all the fire emissions in the first layer of the model. This contributes to inaccurate episodes of air quality.
The weather prediction, while they are getting more and more accurate, there is still room to be improved. For example, we don't know how accurate is our weather prediction in the rural areas. We are designing a meteorological sensor that is only cost $80. Local sensor help us to improve our understanding of satellite data, to what accuracy they have. On top of that, it also allows us to engage the citizen. We basically give those sensors to our citizens. Another part of the research I'm doing is also about the air pollution versus health.
I'm working on new satellite mission called the Maya multi-angle imager for aerosols to study different type of particular like matter pollution and their association with like a human health, like a respiratory disease, etc. We have like 11 cities like around the globe, so it's very, very cutting-edge research. Everybody works really hard and everybody strives to be the best. So we kind of push each other to be the best, and the staff here at Seeger, they are very supporting.
I think that the students are really exciting to work with because they get it. They realize that we have to respond to this challenge. We must change, and in the course of doing so, we can create something positive and an engine for economic development in the future.
The Department of Atmospheric Sciences is part of the School of Earth, Society, and the Environment and is within the College of Liberal Arts and Sciences. The Department of Atmospheric Sciences' vision is simple but all-encompassing, world-class learning and discovery in the atmospheric sciences. To this vision, we teach and conduct research in areas ranging from atmospheric chemistry and aerosols, climate and climate change, cloud physics and radiative processes, convective cloud dynamics and modeling, extratropical cyclones and precipitation, hydrometeorology, hydroclimatology, radar and satellite remote sensing, tropical meteorology and hurricanes, and finally, weather and climate risk.
I am a hydroclimatologist and a hydrometeorologist, so that means that I study the interactions between the land and the atmosphere. What we're trying to do is to understand how deforestation of the Amazon forest could affect hydroclimate over the entire continent. And with help from the National Center for Supercomputing Applications, we visualize this water vapor. My group is particularly interested in extreme events, and I'll give you the example of the Relampago project. My team was the hydrometeorology team. We were measuring the floods, and to do this, we used an instrument called acoustic Doppler current profiler. These boats that you use to traverse along the river, and that's going to give you stream flow.
I study all kinds of different cloud systems around the world. We started in the tropics and go all the way up to the mid-latitudes to try to understand the role of clouds and precipitation in the Earth system. The Relampago field campaign was a field campaign that occurred last spring and summer in the Southern Hemisphere in 2018 to study what we think are some of the deepest and most organized convective systems in the tropics. Our group uses a lot of satellites to measure cloud systems all over the tropics. Being on the ground is really important as well because we can observe the systems with very detailed instrumentation like ground-based radars. The University of Illinois has a wind profiling radar system to measure the wind above the site. It also lets us look at precipitation microphysics, and that helps us constrain models that help us simulate heavy precipitation or different types of clouds that develop different roles in the climate system.
My research focus is developing numerical models that simulate the evolution and the impacts of aerosol particles in the atmosphere. One important metric that we try to capture is the sizes of the aerosols. So there are different instruments that are basically sizing the aerosol particles. But then the other aspect, it's not only size, it's also composition. Some particles form droplets more easily than others, and this has to do with the composition of the particle. Similarly, with the modeling, we need to capture the same properties when we model aerosols as well, so size and composition. And that is challenging because each particle is different, and so that's one of the reasons why we developed this very high detailed aerosol model where we can look at individual particle compositions and track the particles as they are moving through the atmosphere.
My science focus is on climate science, climate modeling, and uncertainty quantification. For the most part, we study how the climate system is changing and what are the impacts for natural and human systems. Some of the climate models we use are very comprehensive Earth system models. We use a model called the Community Earth System Model, which is a very high-resolution atmosphere model at a 25-kilometer grid spacing, coupled to a fully dynamic ocean model. So at these high resolutions, or at these fine scales, the model can produce its own tropical cyclones within the climate system. So what our simulations are finding actually is that there are very close connections between short-term extreme weather events and longer-term climate variability that we're really able to now understand and diagnose using these complex Earth system models.
I do a lot of papers, and probably about half my research is related to climate. The other half is related to atmospheric chemistry issues, air quality. We're trying to do our own part here at the university. I helped develop a new center, the Center for Urban Resilience and Environmental Sustainability. And CURES is really aimed at helping cities plan for their futures, being able to adapt to the changes in climate that we're going to see no matter what we do. We also, as a nation, need to be looking at how do we reduce those emissions that are occurring from fossil fuels. And so I'm also working with people on what kind of solutions might we develop there. Cities and states are still continuing forward. Industry is still continuing forward because they know they have to play a longer game than just one administration. But we do need to ramp it up. And so it's really important that we do something about these changes in climate that are happening.
Students here at the University of Illinois, we try to get them hands-on experience not only in the classroom, on computers and through data science, but also get them out in the field observing weather, because that's really where I think students really get the foundational physics.
We involve our students in all aspects of the research process. For an example, 9 of our graduate students participated in the Relampico field campaign. Additionally, 7 of our undergraduates spent their Thanksgiving break last November helping to collect data. Our hopes for the future is to increase the impact of our graduate program. So we're developing a set of online graduate courses as well as an online master's degree. We also hope to continue to enhance our research and teaching infrastructure. And finally, we hope to continue to take leadership roles in field campaigns around the world to lead high-performance computing initiatives and help with assessments of climate around the world.
Joining us now is Ryan Emmanuel, and he is Associate Professor at North Carolina State University, and thanks for joining us.
Thanks for having me.
Thank you. Can you tell us about your work in bringing the perspective of indigenous communities to the study of environmental systems?
Yes, so there is a small but active group of indigenous scientists, students, practitioners, and allies within AGU. And we try to coordinate to make sure that indigenous voices are heard and our perspectives are included in discussions about science and policy in areas of the earth sciences.
And what about the Native Science to Action program? Can you expand on that?
So this is our 3rd year offering Native Science to Action sessions at the fall meeting. These are poster sessions and oral sessions that feature research and policy work by members of the indigenous community within AGU and by others who are working in collaboration with indigenous communities here in the US and around the world. So that's going to take place on Thursday. We have a poster session Thursday morning with a gallery walkthrough where everyone gets a chance to share their work. And then Thursday afternoon, we'll have an oral session.
And what type of work will they be sharing?
So it's a wide range of work. Some people are working on restoration of culturally important ecosystems with maybe food or medicinal plants in places like the Pacific Northwest. We have people working on projects related to water internationally. We have people working on environmental justice, which is the fair treatment and meaningful involvement of all people in environmental decision making, and an important policy concept.
All right, and also you did a symposium last year, the topic on water research, education, and energy. Can you tell us about that?
We gathered at Salish Kootenai College in Montana for about 4 days in August of 2018. We had about 30 participants to participate in this workshop. We learned from each other. We talked about the case studies that we individually work on, some of the common issues and difficulties of being an Indigenous person working primarily in non-Indigenous spaces, academic institutions, universities, dealing with state and federal policies that may not be designed to prioritize things that are important to us culturally.
All right. Well, thank you so much for your time, Ryan Emmanuel.
Thanks so much.
Now we hit the conference floor and we want to find out who or what inspired you to be a scientist.
What inspired me to be a scientist is I was kind of just doing my generals in my college, which is just like entry-level classes, so you can kind of understand what's happening. And there was an intro to Earth and Space Science, and I took that, and I was like, rocks are really cool. So then I went further with that. So I just kind of went into my field a little bit deeper. I want to work with like community outreach and communicating sciences, just because I don't think that's done really well, and I think that's something really important that everyone could benefit from.
The problems in India related to groundwater, it is actually a crisis in India related to groundwater, so that motivated me to how to solve the problems that, and this brought me here to into the research.
My inspiration into becoming a scientist was probably inspired by a lot of role models in science. You know, important figures that you see as a kid that inspire you. Bill Nye the Science Guy, you know, Neil deGrasse Tyson, these kind of iconic figures that you see that you know, are solving problems by using the best methods that we have available to us.
My mother knew the constellation Cassiopeia's chair. We'd go out and she could point it out and, oh yeah, there it is. And so, I mean, she was the more scientific part of my family.
What inspired me to be a scientist was growing up, I always thought weather was the coolest thing ever, and all my friends thought I was weird because I liked watching the Weather Channel. But now people don't think I'm weird anymore.
The person that inspires me specifically would be my mentor at my school. I go to Allegheny College, and my mentor, I had him for my freshman seminar, and I learned all about the environment and what it meant to be an environmental scientist, and that's what really spoke to me. It really made me think more about the field and what it could bring to not only me, but like people in my community.
For today, remember, we'll be back each day of the meeting with more exclusive material. Have a great day, AGU.